Hey, hello everybody. So welcome back to the world of hybridization. This is part 2 of our hybridization conversation. And so in this one we're looking at sp2 hybridization. That's this guy here, which you can't see. Here we go. So sp2 hybridization. And it's me again, Cameron. And that's just especially for Kuda, because he says he'd like to hear that. So once more, just for you, Kuda, it's Cameron. All right, Cameron. Personally, I think that sounded pretty lame, and I'm not going to make it as a DJ, that's for sure. So, sp2 hybridization. Let's just quickly look back at what we ended up with sp3. So sp3 hybridization had the orbitals, the s2 orbital, the 2s orbital was promoted to the 2p, and this gave us 4 separate sp3 hybridized orbitals. The s orbitals and the p orbitals are atomic orbitals. The sp3 is a hybridized atomic orbital. Okay? The orbital is in between the energy of the p and the s. The energy to promote that s electron comes from the dropping of the p orbitals. We say that the sp3 hybrid orbitals, there are 4 of them, and there are 4 of them which are degenerate. They have the same energy. Not only are the orbitals the same energy, they are the same size and shape, and the shape is like this. It's a kind of mixture of this spherical and this p orbital, and this is called an sp3 hybridized orbital. When it makes a covalent bond, that covalent bond is made by head-to-head overlap of the atomic orbitals. So the sp3 orbital here would overlap with an s orbital from hydrogen. Now this gives us an old-fashioned, what we would call covalent, but now we're going to use the new term sigma bond, and that sigma bond is the direct overlap. There's 4 of them. And because there's 4 of them, it forms a shape known as a tetrahedron. They spread out as far as possible. And the bond angle is 109.5 degrees. For sp2 hybridization, it's just a wee bit different. So let's have a look at that. So in sp2, we still have mixing of orbitals. We have our 2 p electrons from carbon and our 2s. So this is 2s2 and 2p2. However, when they mix, one of the p's decides not to. We'll talk about why that is later. And we're left with the s, which has mixed, and 2 of the p's, which have mixed. Now remember the numbers when we talk about here, we're actually talking about the numerical quantity, not the energy level. So when I say 1 of the s, I mean actually physically 1 of them, not the 1s. I mean 1 of these and 2 of these, giving me 3 mixed orbitals. Okay, now these 3 mixed orbitals have 3 electrons in them, but there's 1 electron remaining in a p orbital. This p orbital is unmixed. It could be anyone, x, y, or z. It doesn't really matter, but for the sake of argument, we'll call it py. Okay? Remember, this is our energy level diagram. Now, remember, the s orbital was spherical and the p orbitals were dumbbells. So again, we have a similar shape to the sp3 one, and we don't really need to go into much difference about why it's different, so you don't worry about that, okay? It's just a big node here and a small one here. Now there's 3 of them, 3 orbitals which have been mixed. And they've been mixed by mixing the s orbital and 2 of the p orbitals. So we call these orbitals sp2 hybridized orbitals. These are sp2 hybrid atomic orbitals. But we have one unhybridized p orbital, which still has the same energy and the same shape that it had before. Okay? Now let's have a look at how these orbitals look like. Here you go. Now again, in the old diagram, this doesn't represent any energy changes. This is just showing you the orbitals mixing. The s and two of the p orbitals, now here it's got the px, py, doesn't really make any difference, like I said. Giving you three orbitals, like this. Now these three orbitals will contain electrons, and they will repel each other. And these will form the sigma bonds that we talked about before. Because they repel each other, they will separate out from each other in a triangular planar orientation, and the bond angle will be 120 degrees. So we say that this is trigonal planar, not tetrahedral like before. These three are separating out as far as possible, and that is 120 degrees. If you try and do it any other way, you won't get that bond angle this far apart. And it looks like this, a triangle. Okay. Now this type of bonding is quite easily shown by looking again at carbon. And so we're going to look at carbon, and we're going to make this an sp2 atomic orbital. I'm not going to show the other node. I'm just going to show the big bulby bit, sp2 and sp2. And remember, the bond angle here is 120 degrees. Along comes another carbon, and this carbon also happens to be, oops, I don't want that color, also happens to be sp2 hybridized. So here we go. Whoop, badly drawn, but there's the overlap, and it's head-to-head overlap. sp2, sp2. Now, you can see what I'm starting to form here. If hydrogen gets involved, then hydrogen has an s orbital, and that hydrogen's s orbital can overlap here, and here, and here, and here. In all of these cases, the overlap forms sigma bonds. It's head-to-head overlap, like we talked about before. To show perspective here, I'm going to use some dots and crosses, or wedges. Sorry, I'm going to use wedges. So that's going back into the board. These are all sigma bonds. Now this wedge is coming out of the board, or the TV screen, or your computer screen, and this one is going back into it, and this one is in the plane. Okay. I think I'll be able to show you a picture of that in a minute. But remember, we have still got the unhybridized p orbital. I'm going to put that up here. So this is a sigma bond. These are all sigma bonds here. Let's see if I've got a picture of that. No, not there. Brian has just come in, so he's going to sit down. I'll try and paint a picture of that in a minute. Okay, so this p orbital here has an electron in it, and this one has an electron in it as well. And they're going to overlap. They're going to stretch over and overlap. And in so doing, they're going to have a stretched and a fairly unstable situation, but it will make a bond. There will be a bond here and a bond here, but we only have one electron. So if you only have one electron, you can't have a full bond above and a full bond below. So you have half a bond above and half a bond below. Now this type of bonding, where the bonding occurs perpendicular, in line with the sigma bond, where the p orbitals overlap by stretching over, is known as a pi bond. So this is half a pi here and half a pi here, and you end up with this. And you show this with a dotted line above and a dotted line below. Half pi here and half pi here. But we usually just show it like this, a sigma and a pi. That's a double bond. The double bond, the two bonds are not the same. And interestingly enough, if you look at the bond energies, the bond energy of the pi bond is not as strong as the sigma. It's not twice, the whole bond isn't twice a single bond. And it's because when we make that pi bond, we are straining here. Okay? We are straining here. So just to review that, the pi bond is formed when p orbitals overlap above and below the existing sigma bond. Okay? And the bond which is formed forms half a pi above and half a pi below. So you never actually get a full pi bond. You always get half a pi above and half a pi below, but we write it like this. And this is shown in eth-in. Okay? That's all, and that's all we need to do. That's all we know. See you later, bye.